Hello again. This is Chris Garvey. I'm going to give the sixth lecture. What I'm going to talk about is just some brief observations about the right kind of sample to make, and give an example of doing an experiment and the aligning up and the setting up of the measurement. So in this talk, I'll talk briefly about samples and substrates, the kind of considerations that you might use before you bring a sample to an instrument. I'll talk about some practical aspects around the setting up of the instrument, importantly the sample alignment, where one defines the measurement geometry correctly, and also some observations about the instrument configuration. And at the end of the talk, I'll give a demonstration video of actually aligning a sample on the Xenox instrument we have in Malmo. So the substrates need to be flat. It's very difficult to define an incident geometry or an incident angle accurately if one doesn't have a flat sample. They need to be flat over a large area, and silicon blocks are usually, or silicon wafers are usually used for this. Silicon blocks are usually used for neutron reflectivity because one can come through the silicon block in the same way that one does for neutron reflectivity, or wafers because they can be easily produced in large amounts. If one thinks about the kinds of surfaces one has on a silicon block, it's naturally hydrophilic. There's some oxidation of the silicon, and there's always a natural silicon oxide layer which becomes silicon hydroxyl groups on the surface, which is hydrophilic. This surface chemistry can be easily hydrophobized with various chemistries. The easiest is silanes. Other substrates are entirely possible. It depends on what kind of surface chemistry you want and how flat you need to have them. Particularly if one wants to come through the solid interface, one needs to have a non-absorbing substrate, and silicon's probably the main candidate when that comes up. I can't think of any offhand. When you're making a sample on a substrate, one needs to also think about what kind of complementary characterizations you can do as well. It's simplest if one does this all on the same kind of sample, or indeed even the same sample. As one needs a flat surface of the substrate, one also needs to coat the substrate fairly uniformly with the sample. One can do this with chemical means. One of the most common ways is spin coating, when one dissolves something in a solution and coats it on the surface. Vapor deposition. We have an example of Langmuir-Blodgett deposition. There's quite a few, but they need to be flat and large. When one thinks about the size of the area that's flat, both in terms of the substrate and the sample, you think about beam sizes. For neutrons, it's indeed a very large surface of the order of centimeters squared. And of course, the larger the area within reason, one can match the beam size and get much more signal. Lab-based X-rays, which we'll see an example of at the end of this talk, millimeters squared. And with synchrotron X-rays, one thinks of maybe hundreds of microns size, but in this case the problem's slightly different, that the X-rays will tend to damage the sample, so one needs some real estate in terms of sample to move around and to mediate the effects of beam damage. This is the instrument that I'll give an example of in a few slides. This is the Xenox instrument down in the basement here in Malmo, it's not so different from a neutron instrument. We're using a copper K alpha source, but there's actually a molybdenum source there as well. So this produces the X-rays. Collimation is simply to define X-rays going in the same direction with very little beam divergence. In this case, we have a sample position, and that can be in air or evacuated, as is normally the case, because the air cores scattering, and of course the signal to noise is much better with vacuum. And further along, we have a tank with a detector that we can move from the back to the front and adjust the solid angle that the area detector covers. This is all in vacuum. And here's the computer that controls it. So let's think about the problem of where to move the detector. It is in the case, as is in the case with transmission sacks, the solid angle determines the length scales that you've looked at. Here I have an example of that we'll talk about at length is a film of LB deposited silicon nanoparticles, and they're quite large. They're 100 nanometers each, the particles. There's a single layer, and if you notice the signal in the middle of the pattern, you can see as you move the detector further back. In the first case, it's at 400 millimeters from this. The pattern gets spread further out on the detector, and so when it's quite close, it's counting much faster. But you'll see, and you can't really see it in this slide here, but there's features in there that are better defined. Here, it's all squashed near the direction of the primary beam, so the features are defined by the fewest amount of pixels. And as you move the detector back further, each feature is defined by more pixels, and this is a much better situation for much more further nanoparticles. Here's another, and in this sense, the detector is sort of upside down. So here's the grazing incidence X-ray scattering signal. So this is the primary beam, and the detector's been inverted. But you can see some streaks here. The advantage of having the detector closer is that you can actually get more streaks on the detector, and these are really quite sharp features as opposed to this. So by moving it closer, if one has more reflections, one can fit them on the detector. So if you move it further back, gradually you'll find that these reflections move off the edge of the detector. Let's have a little bit a closer look at what goes actually in that sample chamber. So here's some samples that I prepared earlier. All I've done is we've got a little platform that can move in this direction, which is X. This direction is Y. We don't move it around that so much. And the direction normal to the silicon is the Z direction, the up direction. We can seal this chamber. Having it under vacuum means more signal and less background, and having it in air means a lower signal and higher background. Of course, some samples, for example, liquid bilayers, will need some water to give the correct despacing, and some samples are quite sensitive to vacuum. Here's the stage with the GiSAS stage without any sample on it. So that's the top here, that's the top here. Z direction is up and down, so we can move it through the beam. The X direction is moving these samples, so we can put a number of samples there and move it along in that direction. And the Y, which we don't tend to use so much in this situation, adjusts the sample to detector distance. There's two rotations, one that you can't see so well, the RY, which is the center is here, and it rocks around the beam. So it means that the sample can be more or less parallel to the beam. The omega direction is quite important, so that's around that direction, and that's just the tilt of the sample in and out of the beam direction. So in aligning it, we need to first of all define the beam parallel with the sample, which is 0 angle, and then we move it with respect to that. And we define that in terms of the Z position and the omega position. And I won't talk so much about it, but sometimes it's not quite so parallel with the RY direction. So this is that situation in a cartoon. This yellow box here is the incident beam, and this is our sample. So we can move it through omega. If we tilt it around this way, it will occlude the beam. If we tilt it down so it's parallel, we'll get the most beam through. And so what we actually monitor is the intensity at the beam center. The Z direction, if we assume that it's parallel, moves directly through the beam. So to align the sample, we monitor the intensity at the beam center. If we, first of all, translate the sample through Z up to cut off half the beam, then rotate the sample around till we get the maximum intensity. If it's too far this way, it will cut off the beam, and if it's too far this way, it will cut the beam, but if it's exactly parallel, you get the most intensity. And we maybe iterate these two steps several times. If the beam is not parallel to the substrate, and we translate across X, if it's a little bit higher at this end, for example, than that end, you'll find that it will change the intensity here. If you have it exactly parallel, this will stay the same. And this is a good way of adjusting the ROI. The other thing I'd like you to think about is the shape of the beam. Mostly we'll be talking about fixed configurations, but in principle it is possible to adjust the shape of the beam by adjusting slits. We can have a wider or a narrower beam, and these have the advantage of being able to modulate the specular reflectivity, for example. Smaller beams, of course, are better for off-speculum and grazing incidents. However, you get less intensity, so there is a little bit of a payoff there, particularly with neutrons. And so let's look at the control panel here. We have different motors, X, Y. There's a picture of the sample. The first thing we're going to do is move the sample through Z. That's up, further away. Move it closer, and we move it as close as we can. The red line on the photo there is the red dot on the photo is approximately where the beam will be. So that's cutting it off. And now we're going to scan through the Z motor, from plus or minus 1, and try to think about what happens as we do that. So it's collecting the intensity as we move the motors an increment. And moving it up through the beam until we cut off the intensity. Okay, so there we have the Z position as the intensity. There's the maximum intensity. And if we move it to the position where we have half the intensity, that's cutting off half the beam. And now we go back to the sample adjustment. Instead of scanning through Z, we're going to scan through omega. And we're going to go plus or minus 2 degrees. That was millimeters before. And we scan again. So we're tilting the sample around the beam. And you might like to think about what that should look like. So first of all, there's quite strong absorption, and as the sample tilts around, you'll see the intensity goes up and up, and the maximum intensity is there, and now it's cutting off the beam again. And we move it to the position where there's the maximum intensity, which is the sample parallel to the beam. And we define that as the angle 0. And everything is an offset from that. It hasn't actually changed the position, we've just defined that as 0. And now we move it to the incident angle for the measurement. So that's the procedure. We'll go a little bit further into the data that we've generated. If you have any questions, you can email me, and I'll see you later. Thanks very much.